In Unit 5, Lesson 1, we learned that trigonometric ratios can be extended to define trigonometric functions. These can be applied to real-world processes. One such function is the cosine relationship of a piston and an engine. A cosine function is a sinusoidal function that starts and ends at its local maximum points. If one considers a unit circle of 2 pi and graphs values of f of x equals cos x at x equals 0, pi over 2, pi, 3 pi over 2, and 2 pi, you'll get a base function that looks like this, and it repeats in a periodic nature. Of the base function, the amplitude is 1, the period is 2 pi, there is no horizontal phase shift or vertical translation. So, why is the movement of a piston in an engine best represented by a cosine function? In an engine, a piston starts at the maximum height of a fixed cylinder. At the top of the cylinder, a fuel-air mixture is ignited by a spark in the engine, causing the piston to travel down the length of the shaft. This motion rotates the car's crankshaft. The piston then moves upwards to its local maximum to be fired down again. We know that cosine functions start at their local maximum if they have a positive lead coefficient, drop to a local minimum, and end at the local max value at the end of the period. We also know that this pattern repeats in a periodic fashion. This perfectly represents the piston firing up and down in an engine. Okay, so let's look at how to set up our cosine function for our piston. A cosine function takes the form of f of x equals a cos k x minus d plus c. A is our amplitude, while 2 pi over k is our period. D is our horizontal phase shift, and c is our vertical translation. Let's take the pistons from my car, the Ford Focus SVT. The height of the pistons of this car is 8.4 centimeters. Given this, our maximum value at the start of our period should be 8.4, because this is the height of the car's piston cylinder. The minimum value should be 0 when the piston is at its lowest point of its cylinder. This is the graph for the pistons moving up and down in my car. Our local maximum at 8.4 centimeters. When the piston is at the top of the cylinder, then it drops to 0 centimeters at pi, which is when it is at the bottom of the cylinder, and then goes back up to 8.4 centimeters at 2 pi, and then it repeats. Notice the periodic nature of this function. It is exactly like a cosine function. Our amplitude is 4.2. To find amplitude given our max and min values, we add the two together, 8.4 plus 0, and divide by 2. Looking at the rest of the cosine function, f of x equals a cos x k x minus d plus c. The next value is k, which we will set to 1 for now because the length of our period is 2 pi. The final value is c, which in our case is 4.2. A standard cosine function has a local minimum value of -1. However, it does not make sense for the piston position to be negative, because then it would be leaving the engine bay. The minimum value is 0. Since my amplitude is 4.2, the vertical translation of c value is 4.2 units up. Putting this all together, the function of a piston in my Ford Focus SVT is f of x equals 4.2 cos x plus 4.2. Now that we have set up our parent function, how can we show that the car is moving faster or slower? As a car travels faster, there are more explosions per second in the engine. As fewer explosions happen per second, the piston will move up and down less times a second. Traveling up and down is directly linked to the k value affecting the period. So, as our car travels faster, then our period should get shorter, because our pistons are moving up and down more times a second. And, as our car travels slower, the period should get longer as the piston moves up and down less times per second. To make our period shorter, we want a k value that is greater than 1. This is because the period is equal to 2 pi over k. So let's graph when my k value is 2. To make our period longer, we want a k value that is less than 1. I can't think of a practical reason why this function can be phase shifted, because a piston always starts at its maximum value, but for completeness of all possible transformations, we can phase shift the function 2 units to the right by making the d value 2. Now that we've got our trigonometric function, let's move on to my second function. For our next function, we will take a look at a polynomial function.
Mario time!
Let's say I race against my dad in my car. He is driving his SVT Shelby GT500. His car is much faster than mine, but being a muscle car does not corner very well. My car is very small, so when we start to add corners into the race, I will begin to stand more of a fighting chance. Could we find a polynomial function that might depict how much of a lead my dad would have on me if we raced one another? In a straightaway, my dad's lead will increase. However, in a corner, I will eventually catch up and overtake him. The base power function of f of x equals x to the power of 3 might help us explain this relationship. Polynomial functions generally take the form of f of x equals a, k, x minus d to the power of n plus c. Let's make our x-axis the total race time in seconds, while our y-axis should be the distance of my dad's lead in meters. Let's assume the racetrack is completely straight until 8 seconds into the race. Firstly, we know that I will overtake my father when the track turns twisty. Given this, his lead will be decreasing. Therefore, we should set our a value to -1/4. This will vertically affect the function over the x-axis, showing how I will gradually pull away from my father on the racetrack. We know that I will overtake my dad when the track turns twisty, so our d value should be 8. This is because the roots of x minus d will be the location of our turning point, while I will overtake my father 8 seconds into the race. We also know that my dad must start braking much earlier than I will to go into a corner, so we will vertically translate our function 2 units upwards. This will translate our turning point up by 2 units, showing how even before the corner I will begin to catch my father due to the increased braking he must do to slow down. This will leave us with the function f of x equals -1/4 x minus 8 to the power of 3 plus 2. This function has a graph that looks like this. We can see clearly that as corners begin to appear on the track, my car will begin to level out with his as he brakes more than I will, before overtaking him at the turning point.